Welcome, ladies and gentlemen, to the first lesson for Pre-AP Bio. As an excellent appetizer, we'll be starting into a chemistry and balancing equations lesson. The goal for this lesson will be to know the purpose of and how to balance chemical equations. Keep this in mind. By now, you should already know that there are essentially two parts to the atom: the nucleus, which is found in the center, and then there are shells surrounding the nucleus. Very specifically, there are protons and neutrons that make up this nucleus, and electrons that move around within the shells. Now, as we mentioned before, the diagram to the right are things that we call models. They're not actually what's going on. Atoms do not act or behave or look anything like what that diagram to the right is, no matter how cool it looks. The reality of atoms are that they are surrounded by shells. We call them that because it's the closest thing that we can call for us humans to understand. In reality, it's a lot more complicated. Electrons are not simply little orbs flying around in space. And when it comes to energy levels, it has a lot more to do with wavelengths and energy rather than actual physical objects flying around. This is important for when you go into advanced chemistry as well as upper level biology, because you should not go in with the idea that atoms are simply little spheres floating around. For us, we won't be worrying too much about this, just wanted to expose you to the idea that atoms and electrons are a lot more complicated, and you should not be going around saying, oh yes, there are simply a bunch of protons and neutrons with orbiting moons and satellites called electrons. The fact remains, however, that electrons do behave well enough within the model of diagrams that we have to the right so that you understand, for now, how they behave. In a very important bit that we're going to cover, electrons can be treated similarly as chemical energy. If you start thinking about it this way, it starts making its connection towards biology. Electrons are moved around in reactions to form bonds. As you can see in the diagram to the right, there are electrons being shared between two hydrogen atoms. This creates a molecule called H2. H2 is actually how hydrogen gas exists in real life. They don't exist as simple H atoms. They actually go around in pairs. And that's because they both need to have two electrons, and the only way they can satisfy that is by sharing those electrons. There is an assumption that by now you should know how to do this specific problem. So we're going to go ahead and take a short break, take a look at this, and see if you understand how to match these up. Okay, hopefully your instructor has paused the video and we can continue now. There are basic types of atom combinations based on the behavior of metals and nonmetals that create these molecules, ionic compounds, and an ion and elements, which is very important to chemistry. This being a review, however, we will continue on this topic at a later time. And now on to the meat of our discussion. A chemical equation describes what happens before and after a reaction. You get something that looks like this, where you have a reactant or reactants before. Then you have a product after. You have a thing called a coefficient, and we'll talk about that in more detail. You have things called a subscript, which is that little 2 next to the H. You have a reaction arrow in signifying a change. And then you have, usually in brackets, a state of matter. If there are any of you, I sincerely doubt it, but if there are any of you who are going, why should we learn about chemistry in a biology class? Please keep in mind, a lot of times content gets separated to make it so that it's easier to study, but in real life, a lot of these are very much interconnected. Chemistry builds a lot of the basis for what we will learn, and it becomes incredibly important and really enriches your understanding of how biology works. As you can see here, one of the reasons is because so much of chemistry becomes what we call organic chemistry. There are sugars and all kinds of biochemical reactions that will affect our understanding of how things work in cells, organisms, and especially the human body. So let's get down to specific note taking. On any exam that we give, we especially need you to know what a reactant is. These are atoms or molecules you start with before the reaction. Think of it like your ingredients for a cook-off, and you need it before in a recipe to make sure that you have everything so that you can create your food at the end. The left side of the equation is where you should be putting them. This is just how we notate things in chemical equations. So in this example, the reactants are before. You have Ag, solid, plus H2S, gas. The products are atoms or molecules that get rearranged by the reaction. Remember that there's that arrow? That arrow indicates some kind of reaction is happening. When you get into a chemistry lab, that's probably the coolest part. You get a flash of light, you get some fire going on, you get bubbles happening, you get some really weird color changes. And that's usually what's happening during that arrow. And so this will be on the right side. Now you're going to get what's left over. As you can see, it's not quite the same as before. Before we had Ag on its own, now it's Ag2S. And instead of just H2S, we now have H2 as a gas. And don't forget, these are the products. Now don't let this intimidate you whatsoever. Those of you who are picking up on this quickly should realize that it's quite simple. Left side is reactants, right side is products. In chemistry, to help scientists make sure they understand what they're writing, there is a difference between saying something like 2H and H2. So we start with something called a subscript. This is a vocab word that we're going to be learning. If you haven't learned it already, in this case, a subscript, like the word submarine or sub-zero, it means below, which is why you'll see the twos highlighted next to H2S, Ag2S, and H2. Subscripts in chemistry indicate how many of those atoms exist in a molecule. It's their combo. There are, on the other hand, something called coefficients. These are the numbers in front of the atom or molecule. And as you can see, that's a coefficient. And you might go, well, that's the only one. If you've already taken algebra or any kind of math at that level, you'll realize that there are, in fact, 3 other coefficients as well. We don't write ones, we simply imply that if I write something down, it's implied there's a single one of them. Anything more than one, I start adding coefficients. So coefficients means how many of that molecule multiplied by that number in front, which we call the coefficient. So let's test your understanding. As a quick practice, how many atoms are in this molecule, coefficient, and the subscripts? We're looking at a single formula here, 3H2SO4. Let's break it down. How many different elements are there? 2. What is the subscript number for each letter? And 3. What is the coefficient number? The coefficients relate to the number of each element. Now keep in mind, you should have had time to work on this. And let's go ahead and begin. There should be 3 different elements. There's an H, there's an S, and there's an O. Very simple. If you overthought this and you started trying to figure things out and add things up or multiply, you're going way, way farther ahead, so good on you. But we're asking some basics just to make sure everyone's on the same page. How many different elements are there? And elements are just single letters or single letters with smaller case letters next to them. What is the subscript for each letter? Well, there's a difference because for H, there's a 2. For the S, even though I did not write a number, again, there's an implied 1. O has a 4 next to it. Remember, it's sub, below. The coefficient number, well, where is it? There's only one. It's the one in front, and so it's the number 3. And now for those of you who went way too far ahead, here we are. Now you want to multiply the coefficient and the subscript number for each type of element to figure out how many atoms there are total. There will be a way we describe this, and that is how many atoms, not how many of an element, not how many of a molecule. So now is when you go ahead and multiply. So 3 times 2, you get 6 total H's. If you look at the letter S, there's only one of them. So it's 3 times 1 becomes there's a total of 3 S's. And for O, it's 3 times 4, so it becomes 12 O's. So here's some independent practice. I prefer this to be group work, so I'd like you to go ahead, if you have someone next to you, to go ahead and discuss what are the subscripts, coefficients, how many of each atom there are, how many elements there are, and then to multiply through and tell me exactly how many atoms there are for each of these molecules. As a homework assignment, feel free to write all these down and practice them. If you are interested in the answers, please go on to the Google Classroom where we will provide the answers and explanation. If any of you have realized we haven't quite talked about balancing equations yet, you are correct. We should be applying what we just learned to a chemical equation in its totality, not just in the coefficient subscripts, but let's look at how this equation works. There's two hydrogen gases, H2 plus O2, which becomes 2H2O. How many hydrogens and oxygens are there on the reactant side? Well, let's count it up. There is 4 H's because it's 2 times 2 and 2 oxygens. So now let's ask a question. How many are there on the product side? And there's 4 H's because it's 2 times 2. And then there's 2 times oxygens 1, making it 2 oxygens. As is being hinted with the little graphic down below, this is due to a thing we call the law of conservation of matter. There's actually quite a lot of different kinds of laws of conservations, so be very careful when you go around saying there's the law of conservation. This one is specifically of matter. It states, in a chemical reaction, matter is neither created nor destroyed. Number plus the type of atoms going into a reaction must be the same coming out. As a brief aside, and this is where I get really excited, this is historically one of the most important discoveries. We went from an age of alchemy, of mysterious chemical equations, not even equations. We were just mixing things up, saying, oh, this is saltpeter mixed with this would cause that. And the people thought of it as almost mysticism. Lavoisier took us into an age of modern chemistry. Lavoisier was a Frenchman in the 1800s who actually decided to push the law of conservation of matter into play. He made the assumption and he made the law saying you can't just have things disappear. Before that, people just said, oh, well, if you set something on fire, you don't get as much of it left afterwards. It just doesn't weigh as much. Lavoisier is the one who said, no, all that smoke, if you could capture all that smoke, it would actually weigh, plus all the ashes, the same as the wood that you burned. And once that's set into motion, it created a revolution in humans' understanding of how things worked. Also, as an aside, Lavoisier lived around the time of the French Revolution. And if any of you are adding 2 and 2 together and wondering what happened to him during the French Revolution, he was definitely no hero. Because people who could tinker around during that time and mess around with flasks and science and all that kind of stuff were generally very rich. It certainly didn't help that he was one of those tax collectors. And so when the French Revolution happened, they definitely cut his head off, which even their rival at the time, England, thought was an extreme pity. Somebody that clever, somebody that monumental to the change of alchemy to chemistry being cut down at such a young age, that was just a shame. Back to what's important for our classroom. If an equation obeys this law, it's considered balanced. And this is one of the most fundamental, and this is why we believe it's important for you guys to pick this up in pre-AP Bio. You need to know that the law of conservation of matter occurs all the time. We cannot have chemical equations happening without it balancing out. So, there are in fact rules for balancing equations. These are side effects, if you will, and notes that we have to make sure you follow, otherwise you will run into trouble with how you balance equations. There are a lot more to explain here, but I'll leave it for when we talk about specific problems and whatever else. But rule number one is subscripts cannot be added, removed, or changed. Think about it like saying you want to remove tomatoes out of spaghetti, right? Or spaghetti sauce. In America, we think of spaghetti generally with tomato. That's not actually what spaghetti is in Italy, but that's okay. We'll pretend we're just Americans. We don't know any better. If you take tomatoes out of spaghetti, it's not really spaghetti anymore. Subscripts are a similar idea. If you take out those numbers or you change them or remove them, or you're just like, I'm just going to mess with it a little bit to help me balance, you have fundamentally changed what we're even talking about. So subscripts cannot be changed. Number two, you can only add coefficients. Do not use the number 0 or 1 as coefficients. They're implied. If it's 0, you don't even write any of the elements at all. And number three, coefficients only go in front of a chemical formula or a molecule, never in the middle of a molecule. Some people will be tempted to do that because it's easier to balance that way. Do not do that. You will mess up the equation. Now note, there is no one particular way to balance equations. Some equations are harder to balance than others and might require some creativity to solve. There is an algebraic way to solve them. Mr. Vo and I are probably not going to teach it. I'm going to mention and show you, especially for those of you who are interested in math. You're just very good at math. And the reason is because the way we're going to solve it is essentially a systematic guessing game. It's fun. It's actually very interesting. And for most people, the way we would go about life in terms of guessing numbers and figuring things out. The algebraic way, however, is a surefire way. It is very effective at figuring out and making sure you always get the correct answer, even for difficult problems. However, the algebraic way does take time to set up, and it does take a certain mastery of math, which is why we're not that interested in pushing this. Most of the problems we'll be dealing with are so simple, you could use the method that we're going to teach you and get away with it. For the most part, using the method we teach you will take you all the way to AP Chem and even some college level chemistry. You should be fine. So now, I like to do this, and keep in mind, I will not be doing this later in the year, but for now, you should have been keeping in mind what it is that you should be learning. And in this case, I'm going to just call this a study sheet, so you're always aware when you see the words study sheet that these are what you need for the upcoming test. Number one, understand the law of conservation. I don't know if I stressed that enough during the lecture, but please understand, you need to know this. I will test you on this. It is so important, not just to human history, but also to your understanding of chemistry. If you don't always think when you're walking into chemistry, there should be some kind of law of conservation, we've not done our job teaching you chemistry. Number two, make sure you can define what coefficients are and subscripts. Now, I specifically write chemical equation because the word coefficient and subscripts are not unique to chemistry. You'll see them in a lot of other places as you continue your academic journey. So I will specifically say chemical equation, coefficients, and chemical equation, subscripts. But for all intents and purposes, if I say, oh, what's a coefficient? We're talking only about this. Number three, identify what a reactant, product, and reaction arrow is. You have to remember that it's on left side, right side, what the arrow means. That's the kind of stuff we're talking about here. And finally, remember the rules of balancing equations. For those of you who've been taking notes, it is important to remember how to sift through when a teacher talks about things. Earlier, I had mentioned things were review. I had mentioned things where, oh, this is stuff we kind of want you to know in preview, but we're not really going to talk about it. And that's how you start figuring out, well, what's going to be important on the test. Notice also that whatever I have written on here actually helps towards balancing equations. Very early on, we actually mentioned what the goal is, and that is to know how to balance equations. Everything else is just dressing or aesthetics or extra knowledge that we'd like you to know. And so this is a skill you should start picking up on and remembering how to do. Eventually, when you're in college, some professors barely even have notes. They have a few squiggles on the whiteboard and talk for an hour, and then you're expected to know what to study for. So this skill becomes very important. For the next parts, your teacher is going to actually demonstrate how these work in class. And this is a method that's called the table method. And we will go ahead and show this live in class. So if you are watching this outside of the classroom, please make sure to either find a Khan Academy video to accompany you on this, or to go in and ask for tutoring with your teacher, or maybe from your classmates to help you out understand how exactly to do this. In general, you're going to draw a line straight down where the reaction arrow is, and you're going to start separating out and listing the reactant versus the product side. As mentioned before, you can't really change much about a chemical equation. The subscripts are locked. You can't do anything about that. However, you can add coefficients. So in order for you to balance it and make sure both sides has the same amount of atoms and elements, you can only add coefficients. So as a quick show, if we were to visualize what we meant by a chemical equation, you'll see that these atoms and molecules do not resemble really what these are. Yes, you can clearly see that there are 4 green circles and 4 red circles and 1 white circle, right? On each side, total. And that's what we mean. There's exactly 1 carbon, 4 hydrogen, 4 oxygens, 1 carbon, 4 hydrogen, 4 oxygens. But they're in a different rearrangement. Chemistry, we'll find, and is very interesting for that's why Lavoisier came up with all this, is that it's just rearranging. You don't lose anything. They're just not destroyed. They're not created, right? There was that belief before. He had to state that very, very explicitly because a lot of people beforehand thought if you had a chemical equation, some things just vanished forever. They're gone. Lavoisier pointed out that no, you might think it's gone, but it's because it turned out it was water, which some people don't even consider really an element before. Others might say, oh, well, CO2 is a gas. I can't see it, so it's clearly gone. So in the table method, we want to make sure that you draw a table down, again, where the reaction arrow is. You're separating the reactants from the products. So on the reactant side, you have, well, there's only nitrogen and hydrogen. And on the other side, you also only have nitrogen and hydrogen. So what you want to do, again, this is a demo in class, is write down how many there were before you start balancing. When you do that, it should become obvious how you would add numbers to affect, again, the coefficient to multiply by the molecules to make them work. At the end, you should remember that it essentially is something to the effect of nitrogen gas plus hydrogen gas becomes NH3. This is in fact the solution for those of you who can take this diagram and understand how it works with the overall equation. You'll know what coefficients to add. So without the demonstration, the best we can do right now in this video is to talk about how, well, there should have been a 2 over here, a 2 over here, 1 and 3. In order for this to balance out, we got to find some way to make it so that this n, instead of being a 1, becomes a 2. How do I do that? Easiest is to multiply it by 2. Now here's the problem. The 2 in front of this n also affects the h over here. This would cause it so that it's 2 multiplied by n becomes 2n, 2 multiplied by h becomes a 6. So what can we do to make sure that this 2, which is also matched up by the 2 now, is also matching up with the h, which is a 2 here, with a 6. This should become fairly obvious at this point. You multiply with a coefficient of 3 in front of the H2 gas, and you get 6 hydrogen molecules, or atoms, sorry. Therefore, it is 1 should be a single coefficient, 1 of the N2, and 3 of the H2s, and then 2 of the NH3s. So now it's time for you to practice. Let's go with KClO3. Reaction line becomes KCl plus O2. Same as usual, write down K, Cl, and O. Do this also for the product side, and start your engines and have fun. We'll give it some time. Your teacher should be pausing at this point, and the solution is 2 KClO3s. You have 2 KCl's and 3 O2s. Let's try another practice. We have C2H6 plus O2 goes to CO2 plus H2O. Now, I'll warn you, you can't tell this, but I can because I do enough chemistry. This is more difficult, for sure, than the one you just did. So let your teacher pause here real quick, work with your groups or independently, and solve this one. The answer should be 2C2H6, 7O2, 4CO2, and 6H2O. This is actually a formative points. If you see this if you're doing it independently at home or with your tutor or whoever else, please keep in mind that in order to score this, you would need a rewritten one. So please see your teacher about a secondary version. This is supposed to be taken as a quiz. In class, however, we're going to simply present this, and you're going to go ahead and try this out. These are presented in the form closer to FRQs than the way we're usually used to. Try these questions out, and we will discuss it as a class, as a partners, and especially with a solution. Since this is the very first one we are doing, there will be a lot more allowances. You'll probably be allowed to redo this right in class. Again, if you're doing this outside of class, don't worry. Just go in and see your teacher. We'll make sure you're taken care of and that you're understanding how to solve these. I will note, especially because you are probably outside of class, your teacher wouldn't have gotten to this point in the class. They would have paused. They should have paused before I explain this point. Don't be intimidated by what you see. Never be intimidated. All of you, every last one of you, are far smarter than you think you are, especially when you see something like this. It's a gigantic paragraph. You're going, what is going on? I've never seen this before. And something like C6H12O6 is a lot more intimidating than just C2H6, right? But it's not as hard as it is. A lot of times it's obfuscating it. It's giving you something that's a lot more intense. But when you start realizing what it's actually asking for, it's not that difficult. So, that being said, good luck. Please see your teacher, email them, talk to them in class directly, and you'll be taken care of for this practice test. This is, in fact, a formative, so it is a grade. Good luck.